Okay, so perfect. So thanks for the introduction, and yeah, thanks again for having me here. It's been a while since I've been here. Today, what we're going to talk, just a quick question. I still see something else on this screen here. Can we switch this, maybe? Okay, so what I'm going to talk about today is a little bit connected to what we've seen earlier today, because I think in the first talk it was mentioned that restricting system calls is a little bit of a difficult problem. And this is something that we wanted to tackle. So first, if somebody wants to contact me afterwards, there's a little bit of contact information here as well, just on Twitter or by email. I want to start with a little bit of a motivation. So a lot of the talks that we've heard so far, they were more on the offensive side. So exploiting memory safety vulnerabilities to get something that you as an attacker might want. So these memory safety vulnerabilities, they are very common. And we might want to target different phases, so we can, at one hand, fix these bugs directly, but in some cases we need to be a little bit more on a defensive side, on a different direction. So we need to employ sandboxing to help limit the post-exploitation impact of these attacks, of these vulnerabilities. Simply so that if we cannot fix the bug immediately, something else can help us stop the exploitation there. As I mentioned, I want to do this on the system call interface. And there are systems already in place to do this. Linux kernel, for instance, provides us with the Linux Seccomp interface, the secure computing interface. It's widely used, so most of the browsers that we run actually use it, as well as Android uses it as well. However, Seccomp has a few problems. First of all, it's a lot of manual work. You as a developer, you must identify every single system call that your application performs, and then create a filter that represents the system calls that your application requires. Now, this is quite easy to do, actually, if you have a small application. But for instance, imagine you want to protect something like FFmpeg. It has over 1 million lines of code. I don't want to go through this and identify every single system call that is necessary there. But thankfully, in previous work, we automated this process. Another little bit of a shortcoming that Seccomp has is that it is stateless. So while it can restrict the access to the system call interface, it only looks at the currently executed system call and verifies whether it is part of this set. So it does limit some attacks this way, but you can improve upon this. And something else that we considered before we started working on this is we also have something like CFI, Control-Flow-Integrity. It allows you to determine or to restrict calls and returns to specific locations. However, with CFI, we can only do this restriction within one domain. So you can apply CFI to a user space application or the kernel, but you don't have any protection that helps limit the interaction between the user space and kernel. So we thought about a few solutions on how we might address these shortcomings. But before I move on, I just want to show you with a little bit of data and also explain a little bit more on Seccomp that these points are actually true. So here we have the number of CVEs over the last year. So we actually see that the number of CVEs issued every year, the number of memory safety vulnerabilities, and so on, keeps increasing. And I also want to thank everybody in here who does offensive research. You are the reason that I can use this slide as motivation for my talk. The number for 2022 is actually from today, so we're already at more than 9,500 CVEs issued this year. Now, brief introduction for Seccomp, simply because I borrow a few of the ideas behind it. In Seccomp, what you have is you have this user space application that you as a developer, you identify the system calls, and you have the kernel. When you start the application, you send these filters to the kernel, and the kernel installs them. Your application is now protected by Seccomp. Upon a system call, the kernel intercepts the system call and checks the filter. You can also do potential argument checks, only no strings or anything you can check due to time of check to time of use vulnerabilities. We've addressed this issue in another paper that we've worked on. But yeah, so you have this filter, you check it. If the system call is not part of the set, so you might be under attack, you terminate the application. Otherwise, it is part of the set. We perform the system call and return the result to user space. So pretty much the same thing as we then, or once the filters have passed, it's pretty much straightforward execution like we've never used Seccomp. But I want to use this small example to demonstrate what is one of the shortcomings of Seccomp. You, as a developer, you need to identify every single system call that is going to happen in this application. It's a small one. It's just going to copy one file to another. And I've spent like 1.5 years now working on topics in this direction. By now, I'm fairly confident that I can tell you what are the system calls that these applications are, or that this application is going to use. But as a developer who's not doing as much work, like working on libc or anything, you might not know what is the actual path that printf takes, what are the system calls that are being executed. So this is really annoying work to do. Just to show you what the system calls are, maybe some of you have a guess what they were. These are the system calls that are being executed, so it's open write, some futex, exit, and so on. Okay, so we worked on this in previous work, so we looked at how can we automate this process. We demonstrated you can do this using LLVM, for instance, to extract the information. And if you want to check on it, we gave a talk on this. It's on YouTube at last year's Black Hat. Now, why am I showing you this? It's a lot of previous work that we've done. It has little to do with what I'm going to present today. There are two reasons. First of all, what I'm going to present today is built upon this work. So we extended it to facilitate what we want to do now. The second reason is pretty much shameless advertising. I'm close to finishing my PhD, and I want to use this to demonstrate what I've done in the past as well. Okay, but let's move on to what we've done and what I wanted to present today. This is a concept that we call Syscall-Flow-Integrity protection. Some of you already might see the connection there to CFI, control flow integrity protection. But with this concept, what we try to achieve is we try to bring a little bit of integrity to user kernel transitions. Our concept SFIP is built upon 3 pillars. As a first pillar, we have a state machine that represents the Syscall sequences of our application. So during static analysis, we more or less extract the information. This system call can transition to these set of system calls. It's a global view of the application. So for instance, we see a fork system call can always be, or an exec system call can only follow a fork system call, or an open system call can then be followed by a read system call. And this allows us to more finely constrain the application. So we're no longer looking at this is actually just a system call that is being allowed, but is it allowed in the context of the previous one? But this is still not a perfect solution. So we can find a better way to constrain this even more. And this is the second pillar. So what we also extract is the origins of system calls. During this compilation, we extract a relative offset of the system call instruction to the start of the function. Why do we use it as an offset? It's simply so that we can work with ASLR. But during this construction, we extract that, for instance, mprotect can only be issued at these 3 system calls in the entire application. So any system call that is then being used at a different instruction immediately leads to process termination, which has some nice additions as well, because, for instance, shellcode attacks are no longer possible if they use a system call, because we've never seen the injected instruction. Now, the first 2 pillars are more or less the information that we extract for SFIP. But we also need to enforce them. This is our third pillar. It's a modified Linux kernel, so we don't rely on Seccomp. It's a full new implementation. And it simply keeps track of what was the previously executed system call, also deals with everything that goes in the direction of what if we have multiple threads and everything. And it simply checks during the syscall execution, is this allowed based on the information that was provided by the application at startup. Yeah, so these are the 3 pillars that SFIP is built upon. There are naturally a few challenges that you need to solve to provide this in an automated fashion. I mean, if we did it like Seccomp and we just said, like, yeah, you as a developer, you're responsible in extracting this information. If you hated using Seccomp, you're going to hate us even more if we don't automate this process. So there are a few challenges. We need to extract the system calls from C functions, which sounds quite easy. We also did this for our automated Seccomp work, but now we need it in a much more fine-grained fashion. We need to be able to determine what is the actual sequence of these system calls. But just knowing which system calls and which order these system calls can be executed in the application is simply not enough. What we also need is we need a precise control flow graph of the application. People who have worked on something on like software-based CFI are very familiar with this. So we borrow a few of the things from there as well. So we generate this inter-procedural control flow graph that allows us to extract the system call, Syscall-Flow of our entire application. The final challenge then deals with a little bit of a weird quirk and like Musel-libc and so on. These are non-bijective mappings between system calls and syscall instructions. Typically, when you compile your application, the system call is, you'll call the system call function, but during the compilation, it's a very small function, you simply inline it. But there are instances where you cannot do this, simply because there are different dependencies in there. So you do have the case where you have a single system call instruction that can execute multiple system calls. And you also need to handle these in an automated fashion, which turn out to be a little bit more complicated. Now, I'm not here to demonstrate just these challenges. I'm also here to show you that we were actually able to solve this. And we did this, we implemented it in a tool that we call Sysflow. It consists of 3 different parts. It's a compiler that's handling the extraction, so it's based on what we've done previously. It's a modified LLVM. And it deals with all the different, the extraction of states, of the state machine, of the origins, and so on. The second part is the library, so we automatically link against that one so that we can send the filters to the kernel. And the third part is obviously the kernel. It's a modified Linux 5.13, I think. Yeah. So in this talk, I will mostly focus on the extraction because the library and the enforcement are comparatively trivial, but still necessary to work. And Sysflow was actually also part of a bachelor thesis from my students. I also want to thank him at this point because we did everything, the entire compiler extraction setup and enforcement and the evaluation, and written a full research paper on it within a month, and it took both of us a lot of time. So I would like to thank him here. So how does this work? The Syscall and CFG extraction is the first part that we need to do. I'm going to use C code here simply because not everybody is familiar with LLVM IR, but the extraction takes place on the IR level. We look at a function, and we have something like here. We have this function foo. It performs some branches in there. It calls some functions, but it also performs a system call. We need precise information what this function is going to do. We need to know every single call target. We need to know every single transition within the function and the system call. And we need to know exact location where this is happening. So this is the information that we extract. We have the transitions. We know, for instance, in line 3, we have this branch that can either go to line 4 or line 6. We can fall through then from line 6 to line 7. We also have the call targets. So something like on line 2, we are going to call scanf, or line 4, printf. There's other information there as well. We also need to extract further information to deal with indirect calls there. But we also extract information on where system calls take place. And we extract this for every single C file. We generate an object file at the end of the compilation. And all this information we simply embed within this object file in a new node section. So the final construction then takes place in the linker. The extraction of the system call offset is a little bit more complicated. We implemented this on x86 simply because we have direct access to x86 and no ARM laptops. And there we had to deal with a little bit of something that's unique to Intel, and that's these variable width instruction sizes. So we need, in the Syscall extraction, we need to extract this as an offset, but we cannot simply count, like on some other architectures, the number of instructions until we reach the system call instruction, then multiplied with the instruction size. Simply because later on, the compiler decides what is the minimum size that I need for instance, a jump. And this changes the instruction size. So in the backend, we take the information from the LLVM IR, like what are the system calls, where do they happen, and in the backend, we iterate over this machine representation of the function and look for system call instructions. We need to extract an offset, so we don't know any address there, we don't know any offset. It's only known shortly before we emit the object file. So what we do is we add this hidden label to the function just before the system call instruction. In the label, we encode information that we later on need because we have no direct access in LLVM anymore to it. We encode the name of the function and what is the system call number that is being used there. Later on, we calculate an address for this label. We can calculate the difference to the start of the function, and we get something like this. We know there's an offset for the function func. At line 02, it performs, for instance, a get PID system call. But we also have here this case with these unknown offsets. And there's a special reason. These are examples of these non-bijective mappings that I mentioned earlier as a challenge. Because in our function foo, we can see here in line 08, we have the Syscall-CP call with a close system call. When we compile this file, we don't know where is the system call instruction. It's in a different source file. So we cannot construct the mapping there. Instead, we simply encode the system call number, what is the function that we call, and encode it as like an unknown offset. We know that the Syscall-CP function is going to perform, I think it's a closed system call in this, yeah, closed system call. And later on, we can find the actual offset to it. So at one point, we compiled, in this case, when we compiled muselibc, the Syscall-CP function. It's written in assembly. We do the same thing. We know the system call instruction, but we don't know what the number is. So we simply encode a 1. Later, we extract the information. We calculate the offset and encode it as like the Syscall-CP function is going to perform an instruction at line 08. So we have these two different parts of information. In the linker, we simply merge them together and we find out our Syscall-CP function is going to perform a closed system call at this offset. Now, we again encode this in the object file that we generate, and we have everything. At one point, we start linking our application. This is where we generate the actual information that we later on enforce. So up to here we only have partial information. The state machine generation is quite straightforward, but also needs quite a bit of time. So we have all these different source files. We just throw them in the linker and generate the state machine. So fairly obvious. But just in case, I also prepared a small example, if this is not enough for everybody, how the construction works. A small example here. We see here the information for the functions. We also highlight where we are currently in the function, the last system call that we've seen, and the state machine. We look at the ordered set of instructions. We see that we have a call to line 56 at this position. And we follow this, so we always recursively follow the instruction that we have. We find out, okay, our function foo is going to perform a system call in line 02. We add it to the last system calls that we've seen, but we cannot generate a state machine yet. So then we also see that there's nothing else happening in there. We only see a call to the function bar1. We follow it as well, using the information what was the last system call that we've seen. And we see that our function now performs a read system call. And we finally add something to our state machine. We see that an open read can be followed by a read system call. We also update the last system call and erase the data, and then we see nothing else is going on, so we return from our recursive visit. Nothing is happening in foo anymore as well, so we again return. And now we are back in our main function. We now call foo2. We follow it, see that there's an open system call happening. So we now add a transition from read to open. We update the last system call, follow again the control flow change, see that there's now in bar 2, there's a stat system call happening. And we look at our last system calls, open now gets a new transition to the stat system call. Nothing else is going on, so we return. We have no information left that we need to process, and we have built our state machine. Now, this is a very simplified example. You can also have the case where you have actual control flow changes within the function. So you have an if-else branch where each side takes, for instance, or performs different system calls, and afterwards there's another system call. So you always need to consider everything that happened before. How do we reach this point? But in the end, you have all this information. You have the state machine extraction. The Syscall offsets in this case are fairly easy because we have generated this mapping to the function. So every single time we visit a function, we add all the offsets for that function that we have. And once we've finished our recursive visit, we have built our final state machine that is now ready to be inserted into our application. We simply add it as a node section, link against our support library, which later on handles all the setup. Now, the enforcement, I will skip pretty much all of it simply because it's less interesting in that direction. It's quite simple, actually. So the library does nothing else than it extracts the information, looks up what is the load address of every single function that is being loaded, and performs the offset adjustment. So now we actually get a virtual address for every single function and their respective system calls that can later on be used. The kernel receives the information, intercepts every single system call, so just like we had in Seccomp, keeps track of what was the previously executed system call, and just looks up, okay, this currently executed system call, if we take the example from before, the currently executed system call is a stat system call. The previously executed system call was an open, so there's a valid transition, and we allow it. If we don't have such a transition, we do the same as Seccomp, we simply terminate the application. One thing that is very important here, that the check of whether the origin occurs or is valid performs independent of the transition check. And this is simply, back when we implemented it, you can more finely intertwine these informations, but we were not entirely sure if the whole concept works in this more coarse-grained fashion. And only lately we've looked into a more fine-grained intertwinement of the information. So this is the idea behind Syscall-Flow-Integrity, but we obviously also need to evaluate it. How does it work? Like Seccomp already introduces a little bit of performance overhead. We also wanted to look at how does our system performs, because now we have more information that we need to act upon compared to Seccomp. So we looked at performance, obviously, always quite important, as well as the added security. The first thing that we looked at in terms of performance was how long does it take to extract the information from an application. We had several applications that were quite easy to compile because we have some restrictions on what we can use. We can only use currently C applications, and they must compile with Musl libc. Simply because I don't want to work on getting glibc to compile with LLVM. So here we can see, if we look at, for instance, FFmpeg, we do have quite a drastic increase in compilation time. But the argument that we have is it's a one-time overhead. I'm not going to use it during development. Only when I'm going to release a new version of my application am I going to enable it. And I don't care if my application is then compiling for like 20 minutes instead of a minute or so. And we also did not optimize anything, so we don't employ any sophisticated caching or something else. The next is then the performance during a runtime test. We looked at various things. So obviously we looked at the Syscall latency of an application when we perform a system call. In our case, we used the get PPID system call. We reported the average and the minimum latency in cycles, and we can see that compared to Seccomp, the combined case, so we perform a system call transition check and an origin check, as well as we also reported the numbers for the individual checks, isn't too bad. So we increased from 294 to 332 in the minimum case, and we outperform Seccomp. So we provide more security than Seccomp at a lower performance cost. A lot of this also has to do with the way that Seccomp works internally. It uses PPF, which is quite complicated. But a micro benchmark is usually not the best way to judge how fast or what's the performance overhead of your application of your concept. So we performed this macro benchmark. We looked at several applications that we've already seen before. We compiled them and tested them. So to perform some typical applications, for instance in Nginx, we just tested how long does it take to process 100,000 requests, or in FFmpeg to convert one file to another. The interesting cases here are the longer running applications like FFmpeg, Nginx, and memcached. In all of these cases, we report less than 2% performance overhead for our concept. PVGen core utils are a little bit of an outlier simply because the way that they work. PVGen is a very small application. We do need to copy a lot of data for it. So a small increase of like 0.02 seconds is already something like 10% overhead in this application. And core utils, we benchmarked all these utilities in their test suite. So there's a compounding effect to all the copying that we need to do. So the longer running applications are more representative of the performance overhead here. But we see that we don't have this big of a performance overhead. But we still haven't talked about the security that we provide. In our security analysis, we looked at several things. Like, obviously, one thing that is quite interesting is, how does the state machine look? How many average transitions and so on do you have in large-scale applications? And this is the first thing that we looked at. So we compiled all these applications, extracted the state machines, and counted what's the average number of transitions per system call that we identified. The number of states here on the right side, as we can see, is, for instance, the number of system calls that you have to enable for Seccomp. The one that I would like to pick here is Nginx. In Nginx, we have 108 system calls that must be enabled for it to work correctly in all cases. With Seccomp, we don't perform any transition checks, so every single one of them is unconditionally true. It can always be executed. So we have, for all of these 108 system calls, we have 108 possible transitions. When we now look at our implementation of SFIP, we can see that we can reduce this number from 108 possible transitions per state to roughly 66. Now, 66 is still a huge number, but compared to Seccomp or even an unprotected application on Linux 5.30, you have 357 system calls, and every single one can be executed at any point in time. And the numbers that we report here should also be understood as a bit of an upper bound of an application. We do have quite a bit of over-approximation in our solution, simply by the way how we handle indirect calls. So we handle it the same way as CFI does it. We simply pattern match upon an indirect call the function signature of the calling function with the one that is being called, and this leads to quite a bit of over-approximation. But still, we do reduce the attack surface quite a bit in this case. The next thing that we looked at is the origin analysis, and the previous slide here is also quite important. When we again take a look at Nginx, we see that in total we have 318 system calls in there, where we have 318 system calls where we were able to extract an offset from. This does not include any underlined syscall instructions. In a Seccomp, for instance, every single one in Nginx of these 108 system calls can be executed at every single one of these 318 locations, plus every single underlined system call instruction that you can find. When we do enforce these origins in our system, we can see that a system call on average can only be executed in 3 locations. So we have this protection through the origins and the transitions. And if an attacker performs, for instance, a system call that doesn't belong to this system call instruction, it's simply going to be terminated. Now, one thing these are some numbers that are quite important, but I also want to discuss a little bit the implications our system has on some control flow hijacking attacks. And the one that I picked is return-oriented programming. Now, I realize that most of you are very familiar with ROP, but just a little bit of a primer that I want to give you. In a ROP attack, you use existing code to exploit the program. For instance, with data execution prevention, you can no longer use directly shellcode that has been added to your application. You need to find a way to make it executable, and you do this via system calls. So in a ROP attack, you jump to parts of a function, the so-called gadgets, and try to get what you want, to achieve a task that you want. These gadgets are always these assembler instructions that are followed by a ret. We have here a few examples of them, for instance, like the syscall followed by a ret instruction. To perform the attack, you chain these together, and you get a fully functioning exploit. And to start the attack, you overwrite the stack pointer, so you need some memory safety vulnerability. You prepare the stack and simply call ret. A brief illustration of this as well. So we have a stack here, we have the program code, and some registers. We have already prepared our stack, and we also have the program code here. So we start our attack, we return, jump to the first gadget location. This is simply used as a trampoline so that you get to the second location. So we call ret again, get to our gadget 2, where we pop some values into the registers. We do this, call ret again, and perform the system call with the parameters that we have prepared in our registers. And this is just a simple example of a ROP attack. Now, these gadgets, they are not maliciously put there by an application developer. They are just often unintended. So when you consider the byte sequence, so these are x86 instructions. When we disassemble this, it simply disassembles to an add instruction that adds a constant value to our register. But when we skip the first byte, we get something entirely different. So these are these unaligned instructions that we have. We get this very nice ROP chain through it. There are several tools that help you. Most of you probably know them already. But the property that we exploit here are these non-aligned variable width opcodes. The Syscall instruction is even easier to find. It has a very short byte sequence. It's only OF05. I can find this quite often in large applications. I mean, FFmpeg has over 1 million lines of code. There's a lot of opcodes when you compile it, so quite easy to find. Now, what is the impact that our concept of SFIP has on these return-oriented programming attacks? There are several restrictions that we impose upon its attack. We do not eliminate these entirely. I'm never going to claim that this is a perfect solution, but there are some restrictions that we have. For instance, the Syscall origin check allows us, for instance, to entirely eliminate unaligned instructions. So exploiting them in a ROP attack or even a shellcode attack is no longer possible. The second restriction is that not every sequence is possible anymore. You as an attacker, you must identify before you start your attack what was the previously executed system call. Am I in a point where a transition to my system call that I require in my attack is possible? So to conclude this, we can say that SFIP imposes significant constraints, but it's not a perfect solution. Especially when we consider a certain type of attack that we know from intrusion detection systems. And these are these mimicry attacks. In intrusion detection systems, you have, for instance, you also rely on system call sequences to monitor for weird behavior, I would call it. And you have this detection policy where you look at, if I see a sequence of open fstat right, arbitrary selected system calls, then this is part of an exploit. It's malicious behavior. In a mimicry attack, what you try to do as an attacker is you start with your open system call, you add some no-op system call, then call fstat, insert another no-op system call, simply to evade the detection that you have. And something similar can be done to circumvent our attack, or our concept. Instead of invading a detection, what we try to do with a mimicry attack on SFIP is we try to get to a point where we can actually execute the system call. For instance, consider an application where we exactly need this sequence that is open fstat right sequence, but open, for instance, has, based on the analysis of the application, no transition to fstat. So we can never perform this because we will be immediately shut down. Using a mimicry attack, we use information that we have on the state machine to get from an open system call to another system call that then allows us to get to fstat. And we can also repeat this multiple times to perform an attack. However, as an attacker, you need significant knowledge. What is the state machine? Where are the system call offsets so that you can perform this attack? Because at any single one of these transitions can be blocked either by the origin check or the transition check. Now, before I conclude my talk, I want to point to something that's going to appear probably in the near future, so a couple of months away probably. And this I would like to illustrate in this case. So when we look at the information that is extracted in our SFIP, we have a case like this. We have a location A, it's performing a system call, open, and then calls a function bar that performs another system call, read. But we also have another location where we have the system call open again, but we call bar2. And there we perform a system call stat. On the right, we can see here the information that we extract. We extract the information that open can transition to read or stat. So we have this global view of the system call of the Syscall-Flow of our application. And we also have the origins which are checked independent. Due to this independent checked, I like to refer to this version of SFIP that we have here as coarse-grained SFIP. Some of you might be familiar, we also have this in CFI where you have coarse-grained CFI and fine-grained CFI. So what I've been working on the last couple of weeks is a modification to SFIP that brings us from coarse-grained SFIP to more fine-grained SFIP. And we achieve this by doing a more finally intertwining the offsets, instead of checking them independent, we now generate our information in the state machine in a way that entirely links the transition to the offsets of the two involved system calls. So in this case, the open system call in foo1 can only be followed by the read system call in bar 1. We can no longer make the cross to a different location. And this allows us to do a little bit more fine-grained CFI, or SFIP. Now, we also have a proof of concept. You can find it on GitHub. Right now, it's a little bit more complex to use. At one point, I intend to open source my entire toolchain that allows you to compile every single application that runs with muslibc and is C-based. But this will probably take another couple of months. There are also more details that you can find in the paper, so we have a lot more implementation detail. We have a more extensive security discussion. We also demonstrate a real-world bug, where we demonstrate that this bug would have been prevented in this application if we apply SFIP. To simply recap what I've talked about here, with SFIP, we provide a little bit of integrity to these user kernel transitions that we previously did not have with Seccomp, a little bit with Seccomp, but CFI. We also provide security by checking the syscall transitions and also the origin of system calls. And I also want to highlight that SFIP, the way that we currently design it, it is fully automized. If you get the toolchain to run, you can use it in systems. I'm not going to guarantee that it works. It's a research prototype after all. We took some shortcuts. And it has, for the security that we provide, for the reduction attack surface, it has a very minimal runtime overhead of less than 2% in the applications that we demonstrated.